Welcome, class, to Chapter 15 of Burge and Overby's Chemistry Atoms First, 4th edition. Yes, we are jumping into Chapter 15. We are, for now, skipping Chapter 14. And the reason why is 14 is all about kinetics. And kinetics, in my opinion, is a little bit easier to understand if we've already talked about the contents of Chapter 15, which is spontaneity, entropy, and free energy. We can use these topics to better understand the reaction rates and kinetics mentioned in Chapter 14, though yes, they can be disconnected and taught in the opposing order, like how the textbook has it arranged with kinetics first. In my opinion, it's easier to talk about thermodynamics part 2 first, since it's really, like, Chapter 15 really does piggyback off of Chapter 10 in combination with all of the phase studies that we have talked about so far in this spring semester. So let's jump into spontaneity by definition, as well as what entropy is, because this may be a term that's a little bit more familiar to you, but maybe here you'll be learning to see it in a different way, in a more meaningful way. So entropy, if you've heard this term before, is oftentimes referred to as the randomness of the universe. This is not true, hence why I have this big ol' red X through the word randomness. Entropy can appear to be randomness, but in the great world of cause and effect, randomness does not occur, or randomness does not cause entropy, but entropy can appear to cause randomness. All right, well, if entropy is not just a measure of the randomness of the universe, what is it? Entropy is a measure of the dispersion of energy at some particular temperature at an instance in time. In other words, entropy is all about probability. How likely is a particular reaction occur? What are the odds of an event occurring? Observationally, this is what we are looking at, is the statistics of something occurring. What are the odds? How can we measure these odds? Physically and chemically, what entropy is a redistribution of energy. For instance, if we have a particle that has some given internal energy E, as it moves throughout the universe, or as it's trapped within a crystal, or as it's undergoing some type of chemical reaction, this energy is going to be lost in some way, right? The particle does not exist in a vacuum. It is constantly exchanging energy in some form with the universe, and is oftentimes radiating out its excess energy. So we can think of an entropic process, one with which entropy is involved, is like the heating of the engine in your car. An engine is designed to use combustion, right? At least in our modern combustion vehicles, as I am recording this, these vehicles are designed to use combustion to harness that energy to propel your car to move forwards. They are designed to take chemical combustive energy and translate it into kinetic motion. However, the engine in your car, this is my little engine right here. It's a terrible looking engine. As the engine in your car continues to work at this process, not all energy in is directly converted into energy out, right? Not all of our combustive energy from my little flame here is turned into kinetic energy. There's always a little bit of energy that's lost in the process. And in combustion engines, this amount of energy observably lost can be seen to be lost through heat. If you ever put your hand on the hood of your car after you've been driving for a while, you will feel that it is hot. And this is because there is a little bit of energy lost from your engine as it was converting the combustive energy, the chemical energy, in other words, to kinetic energy. This is entropy. This is a redistribution of energy. It is always occurring whether we are able to observe it or not. Sometimes the energy transfers aren't always going to be heat, but this is what entropy is. As any process continues forwards and energy is involved, a little bit of energy is always going to be lost in the process. And again, if we connect this to statistics, the odds of energy in being converted purely to energy out is a very low probability of occurrence. It is more likely that energy is not going to be trapped in one process, but rather that energy can be lost. If there are these diverging paths along the journey to get energy from combustion to kinetic, well then the energy is going to take any number of those alternate paths because it is likely to occur. All right, and that can be a little bit tricky to think about. Like, that doesn't really explain why the energy is going to be taking these alternate paths, but rather just observationally we see that it does. Again, if we think of this in terms of probability, we can get a better understanding why it is that energy disperses in this way. So for example, if we look at the illustration down below, what this gentleman is doing is throwing bricks. Why he is? I don't know. That's his own imperative. But if he's throwing bricks to the left, we can see that this illustration demonstrates that the bricks are falling in this perfect stack. Well, he's not conscientiously placing them there, he's just randomly throwing them there. And this is not to say, obviously, that the bricks can't randomly fall in this way, but it's a very, very improbable way for the bricks to fall. It is not likely that if you're just haphazardly randomly throwing objects that they're going to perfectly stack like on top of each other in a really nice, and to us at least, apparently organized way. There are fewer ways to stack bricks in this organized way. On the right-hand side, you can see what is the more probable way for the bricks to fall. If you're haphazardly throwing these bricks, then they're going to haphazardly fall on the ground. There are more ways for these bricks to quote-unquote stack in a disorganized way versus the organized way before. Now, we're not saying that it's impossible in the universe to like stack bricks in a really nice organized way. Obviously, like, houses exist, buildings exist, walls exist, with bricks in a very nice and organized pattern. The difference here is the intention of the placement. If you are not intending for the bricks to fall in a very specific and organized way, they're not going to, right? You need to intentionally place things in order for them to be nice, neat, and organized, because the odds of occurrence state that if you are haphazardly throwing bricks, they will land haphazardly. When these bricks are thrown haphazardly, there are more ways for them to fall, and therefore they will fall in any number of these ways. Again, it's not that if you're haphazardly throwing bricks, they can't land in this really nice organized stack, but it's rather to say that the odds are against you. Another way to think about this is the card game 52 card pickup, if you've ever played that, where you take a deck of cards and just throw it in the air and see where the chips may fall, or literally where the cards may fall. If you take a deck of cards and throw it in the air, yes, technically, they could all come back together and land on your desk or land on the floor in one perfect stack of cards. However, the odds are against you that that will happen. And the odds are not against you because the universe prefers randomness. The odds are against you because the odds are against you. There are so many moving pieces inside of this deck. Literally 52 cards if you're playing 52 card pickup. And the odds of each one of those cards following the exact same trajectory from being in the air down to being on the ground, fighting things like wind resistance and kinetic motion, like those odds are so astronomically low that they would land perfectly. However, if each card is allowed to act of its own accord, to be influenced by things like wind resistance and kinetic motion and temperatures and turbulence and all of these things, then each of these individual cards will find a more probable place to land according to its own journey. This is what entropy is. It's not about increasing the randomness, but it's about following the odds. What are the odds that something is going to occur? So let's talk about the man who discovered entropy and started quantifying it for the first time. Ludwig Boltzmann, who lived from 1844 to 1906, was the man who started putting numbers to this concept of entropy, where entropy, he found, is dependent on the number of degenerate ways that a system can be rearranged. Right, so again, it's all about the odds. How many places can, let's say, those 52 cards exist after you throw them in the air? Well, they could fall anywhere on the floor, so what are the odds that they would land in any one particular place? Statistically, entropy, which is measured with a variable of S, is equal to this constant here, known as the Boltzmann constant, appropriately named after the man who was working on studying entropy, times the natural log of W, where W is the number of degenerate ways that your system can be rearranged. And that can be a little bit tricky to quantify how many different ways a system can be arranged. So let's explain it in a really easy, straightforward way. Very simple example. Let's say you have 3 balls, ball A, ball B, and ball C. How many different ways can you rearrange these 3 balls? Well, we can see here the first example, the first set that we have is ABC. Well, we can also write this as BCA. We could also write this as BAC. We could also write this as CBA. You get the point. Like, all of these different ways that we can rearrange and write a unique set of these 3 different balls, which I got lazy and stopped writing these circles around here. So far we have written 4 different W's, right? 4 different ways that the system can be rearranged. The greater the number of rearrangements, the greater the number your entropy will be. So this also kind of helps to explain why it is that the entropy of 52 card pickup, or that those like piles of bricks being thrown, was so great. So entropy is all about, again, the odds. What are the odds of something happening? The greater the number of rearrangements, or the greater the number of positions for your pieces, the greater the entropy will be. And numerically, last but not least, we can see what Boltzmann's constant is equal to. Little k sub b with the capital B here is equal to 1.381 times 10 to the negative 23rd joules per Kelvin. So we can see that there is an energetic component to entropy, hence the joules here. This is an energy unit. And this entropy is also going to be dependent on temperature, since we have a temperature unit here. So it's like energy per temperature unit. All right, so let's talk about W a little bit more, right? W, I did say, is sort of like the means of measuring how many ways a set or a set of particles can be degenerately written. W is also known then collectively as a microstate. So one of those brackets of A, B, C written on the previous slide is known as a microstate. This is one set of arrangements. A microstate is all of the unique quantized energy states that are occupied by all of the atoms in a closed system at some instant in time. So this is a really technical definition, but really what we're looking at is the discrete number. Since this is what quantized means, we're looking at the discrete number of energy states of the system. So occupied by all atoms in a closed system at instant in time. We can kind of just wrap up in one thing by saying we're looking at all of the unique quantized energy states of the system. All right, so we're going to define our system here, our example, down below. It's a pretty straightforward example. It's definitely a simplified example, but the same rationale of this example down below can be applied to larger systems that we're going to be talking about later, like chemical reactions. All right, so a microstate, and how we can find the total number of microstates, statistically speaking, is we are going to take the number of positions of these particles, like let's say the number of positions on the floor that cards could land in 52 card pickup, and we're going to raise it to the number of objects. So this would be like the number of cards in your deck for 52 card pickup. So we can see the relationship between X, the number of positions, and N, the number of objects, in this statistical equation down below, where W, again, is the number of microstates we're looking at, the number of degenerate ways that all of our particles can be arranged, which is equal to X to the N. All right, so let's get a good visual example for this. What does all of this mean? So let's say we have 3 particles, A, B, and C, and we're going to release them into this large box that has 4 different chambers inside. Our question is, how many unique ways can we place A, B, and C inside of this large box? Well, one possible state of existence is to put A, B, and C in the same box up in the upper left, or the same chamber in the upper left of this box. So this would be number 1. This is one of our microstates. Well, the second way that we could arrange them is to move all B and C into, or all of A, B, and C into the second. This would be position number 2. Let's say we could hypothetically say A, B, and C, so we're going to spread them out. Or we could say A and B and C. Each of these additional arrangements would be number 3 and number 4. So our goal is to find how many total ways could we place all of these particles, all of these balls inside of the box with 4 chambers. Now again, we could think of this relative to 52 card pickup, only instead of playing 52 card pickup, let's say we're playing 3 card pickup. Our question is, if this is the floor and we've just arbitrarily drawn 4 tiles on the floor, where could the cards land? Well, the cards could all land in the same tile at the same time. They could spread out. We might have 2 cards in one place, one in another. This is exactly what we're looking at when we are counting the total number of microstates. How many total ways could the cards have landed on the floor? Now, yes, the number of 4 chambers here is kind of arbitrary. We could have drawn more if we wanted to get a better measurement of how exactly the cards could have landed on the floor. However, this is supposed to be a general example, right? Something that we're using to understand the concept of what a microstate is, and we can expand it later into the more complicated systems. Well, our question here is, how many total microstates are there? How many total ways could we uniquely draw A, B, and C inside of each of these chambers, where I have 4 possible illustrations written right now? Well, we could spend our time to write out and illustrate all of the options, or we could use this equation to calculate what the total number of microstates is and save us a little bit of time. All right, so we're going to take the total number of positions to be equal to our x. This is the 1, 2, 3, 4 chambers in this box, or the 4 tiles on the ground. So we're going to say that we have a base of 4. So we are going to take this 4 and raise it to the power of n, where n is the number of objects we are working with. We can see we are working with a total of 3 objects, balls A, B, and C. So the total number of microstates we would calculate is 4 to the 3rd, or 64 different total positions for where these things can be placed inside of this box. Now, because there are 64 different possible outcomes, going backwards again to talking about entropy, this means that the system is going to be relatively entropic. There are so many different ways that the cards could land, which means we can plug the 64 into the equation to figure out exactly how much entropy this system has. Now, thanks to the Boltzmann constant, which is a very, very small number, we can see that the entropy value here, if we were to actually crunch these numbers, is going to be incredibly small. If we want to find entropy in terms that are a little bit more macroscopic, we can always scale by Avogadro's number, 6.022 times 10 to the 23rd per mole, to get a unit of entropy that is going to be in joules per Kelvin mole, and the resulting number is going to also be a little bit more macroscopic as a result. But the takeaway message here is, if we know the possible number of microstates, our W, we can plug that W into this statistical equation to calculate what our entropy for the system is. Whether the system be as simple as 3 balls being thrown onto 4 different tiles, or whether it be as complicated as 52 cards being thrown into the air, where could they land on the floor? All right, so let's look at another example of being able to quantify entropy. So let's say we have 100 argon atoms. They are released in a box with 4 different chambers. The question is, how many microstates are possible in this system, as well as what is the entropy of the system? Aha, we can see here, in joules per Kelvin mole. We are looking for a value of entropy that is a little bit more macroscopic here on a per mole basis. So I'm going to let you guys process this information. work through the problem, figure out how much entropy we are actually working with here. All right, welcome back. Let's determine how much entropy this particular system has. And again, we're thinking 100 gaseous atoms that are free to move around inside of a box that has 4 chambers inside. These 4 chambers are arbitrarily drawn. These argon atoms are free to go wherever they are going to go. And so as a result, we can assume that there are going to be many microstates available, many possible placements for these argon atoms inside of the box. And because of the great number of positions that the argon atoms can occupy, we're also going to have a relatively great amount of entropy as a result. All right, so our first question is, if we have many microstates, how many do we have? Well, to find the number of microstates we work with, we're going to use our W is equal to x raised to the n to find it, where again, x is the number of positions we are working with. So because we have 4 chambers provided, there are 4 total positions for these particles to be in. And we are going to raise the 4 to the exponent of how many things we are working with. And because we're working with 100 argon atoms, that's going to go into the exponent. All right, so 4 raised to the 100, if your calculator can actually process this number, ends up being equal to 1.6 times 10 to the 6d. Now this is a unitless number, this is just a counting number. Again, how many possible arrangements could we have for all 100 argon atoms? Either all 100 could be in the first chamber, or they could be split 50-50 between 2 chambers, or they could be spread out amongst all 4 chambers. And as these argon atoms continue to exchange positions with each other, we can see that there are a grand total of 1.6 times 10 to the 60 total microstates that could exist. This is an incredibly large number of positions, not just like positions that an individual argon atom can occupy, but again, 1.6 times 10 to the 60 total number of degenerate arrangements inside of the box across all 4 chambers. All right, and this is just with 100 argon atoms. Imagine if we actually had a meaningful macroscopic sample of argon atoms. This number of microstates would be even larger. But that's not the question here. The question is, if we're assuming we have even just 100 argon atoms and put them in a box, what is the entropy of this system? Well, we can use Boltzmann's equation. The S is equal to Kb times the natural log of W to figure this out. So we're going to take Boltzmann's constant, which is equal to 1.381 times 10 to the negative 23 joules per Kelvin. And we're going to take this and multiply it by the natural log of our W, which is 1.6 times 10 to the 6d. Now, as we crunch these numbers, we find that our initial S, our initial entropy, ends up being equal to 1.9 times 10 to the negative 21 joules per Kelvin. So this seems to be, like for having such a great number of microstates, a relatively small amount of entropy. And here's now where we can draw a parallel to enthalpies and energies. Remember that if we're working on the atomic scale, our energies oftentimes end up being on the magnitude scale of like something times 10 to the negative 19, times 10 to the negative 20, maybe even times 10 to the negative 23. So if we want to take this entropy and scale it up to a like more macroscopic quantity, what we need to do is use Avogadro's number to get this into a per mole unit instead of a per atom unit. All right, so we're going to take this 1.9 times 10 to the negative 21 joules per Kelvin and multiply it by Avogadro's number, as I've previously said that we should do. We're going to take this and multiply it by 6.022 times 10 to the 23rd per every 1 mole. So this is again kind of like the atomic equivalent to saying like, okay, well, each individual set of argon atoms is going to have this entropy. What if I have a chemist's dozen of argon atoms? How is that going to impact the energy? So we're just going to scale it up by Avogadro's number and find that the total amount of entropy in our system is 1.14 times 10 to the 3rd, or approximately 1,000 joules per every Kelvin mole. Entropy is not just a measurement of randomness in the universe, but rather a measurement of the odds of occurrence. How many different positions something can take up, how its heat is going to be distributed. In this type of calculation here, using Boltzmann's equation, we can see that we are literally just observing the statistics of how many, or we are literally observing the statistics for how these argon atoms could be arranged. Now, they could appear to be randomly distributed, they could all appear to be in our first box chamber, but the total number of microstates is an astronomically large number. So being able to predict where all of these argon atoms would be at any one instant in time is going to be literally impossible for the human, like for an individual human to be able to do. So instead, we wrap all of the chance, all of the statistics up into one calculation and say, well, our system is going to have 1.14 times 10 to the 3 joules worth per Kelvin mole of entropy. All right, so this brings us to what has been observed to be the third law of thermodynamics. Since the entropy of a system is related to the number of microstates that the atoms or the particles or the cards or the bricks can exude, as it turns out, entropy does exist already on an absolute scale. It's not relative to anything, like enthalpy is. The third law of thermodynamics states this concisely by observing that the entropy of a perfect crystal is going to be zero at absolute zero. And why this is can be understood by observing Boltzmann's equation. If there is a perfect crystal that does exist, perfect crystal meaning that all of the atoms inside of your crystal do not move because you are at absolute zero and there is no atomic motion, there's no wiggling, there's no energy being distributed or being pushed kinetically from one place to another. If everything is perfectly still, you can only have or represent this with one microstate, one snapshot. Particle A is stuck in position, particle B is stuck in position, particle C is stuck in position, and all of their internal energies are stuck within them as well. We represent this through acknowledging that there is only one microstate, one W. It doesn't matter how many particles we are working with, whether it be 1 or 2 or 3 or a million, because there's only one position for them. And if we take 1 and raise it to any exponent, we're still just going to get 1. And if we take this W that is equal to 1 and plug it into our Boltzmann equation, the natural log of 1 is just equal to 0. Therefore, the entropy of a perfect crystal with no motion, everything stuck in place, everything locked in time, is going to be 0 at absolute 0. And again, this observation of the third law of thermodynamics states, or implies, that entropy, again, is not relative like how enthalpy is. Again, enthalpies are all defined relative to the elements in their natural states. Right, where again, like gaseous oxygen has an enthalpy of 0, or solid gold has an enthalpy of 0. And all of the other chemical formulas and molecules and compounds are relative to the elements in their natural state. The other implication, though, of the third law of thermodynamics is that standardized entropy values for any particle or any compound are always going to be positive. Notice that our variable here does not have a delta value. This is because, again, standardized entropies for a particle or a compound are not relative to anything. There is no change measured here. There is one individual entropy value measured for a particle, and this number is going to be positive because the entropy will always be greater than that at absolute 0. Okay, well, before moving on to observing the entropy of the universe and how it connects to spontaneous reactions, let's get a sense for how we can observe and think about entropy more qualitatively now that we have defined it in more technical terms. Right, so now that we have that technical background, what's the big takeaway message for how we can think of entropy in particular systems? Well, we'll first observe the atomic mass and the molar amount relationship with entropy. In the first, we can see it is stated that entropy increases with the number of subatomic particles that we are working with. And second, it states that the entropy increases with the number of particles you're working with in general. Both of these things can be understood, like both of these statements can be understood, by thinking back to our microstate equation, where the more stuff you have, the greater your number of microstates. This is true whether or not we are looking at subatomic particles inside of an atom, or whether or not we are looking at the number of particles we have inside of a container. If you have more stuff, you're going to have a greater number of microstates, and if you have a greater number of microstates, you're going to have a greater entropy. So if we are just comparing, let's say, which of these two atoms would have a greater internal entropy? Something like lithium compared to gold. We would say gold is going to have the greater relative entropy because it has a greater number of subatomic particles, and therefore a greater number of internal microstates that can exist. Next up, we're going to look at phases. So the phase of a material, as well as the temperature of the material, can be thought of also as being connected to entropy. Let's talk about phase first, then we can incorporate temperature, since the two are also kind of related to each other and how we think about their connection to entropy. Well, the phases of matter that we are going to consider are solids, liquids, and gases, and each of these in turn leads to a greater amount of entropy. The reason why is not necessarily because we're changing the amount of stuff we're working with, but in this case we are changing the number of positions that that stuff can exist in. See, in all of the previous examples thus far, we've just been like arbitrarily drawing like chambers and boxes, and it's like, yeah, but like, why do we do that? Like, that just seems so random, that seems so arbitrary. Well, what those chambers are supposed to represent is where the particles may viably exist. So for example, if we're looking at a solid, we can see that it is contained within a very specific volume, it is holding a very specific shape, and we know that particles inside of solids do not move easily. Like, they will certainly be vibrating, but they may not necessarily be exchanging positions with each other, and even if they do, the number of positions are going to be stuck inside of this cube right here. This means that we're going to have a relatively low number of positions where these particles can exist in, and therefore a lower entropy. If we compare this in the most extreme all the way over to the gaseous example, where each of these particles now is able to freely move independently, well, we can draw the same number or the same types of like boxes over here, but because these particles can exist in greater numbers of locations, the volume here with which they can move and occupy is greater. Well, this means that the number of positions they can exist in is greater, and therefore we're also going to get a greater entropy. Right, so this is what the quote-unquote positions measurement is all about. How many locations could these particles exist in? What's the volume with which they occupy, and how easily can they move around within these positions? And as we turn our attention from phase to temperature, well, temperature we know is just a measurement of molecular motion. So if we're giving these particles more motion, this means that they can get to more positions more easily. Even in the case of a solid, where the particles inside may not move very easily, if you heat up the solid, then chances are the vibrations are going to increase. We might actually start seeing some particles like swapping places with other particles nearby, particularly if it's a pure substance. That would not happen with ionic compounds because of charge specifications. But the point is, even if you're locked within the same phase, an increase in temperature is going to give you a greater range of motion and therefore a greater entropy. And last but not least, we can talk about structure. Specifically, we're going to be looking at the structures of molecules here. Observationally, the entropy of a structure is going to increase with the size and complexity of the structure. So for example, on the left, we have a smaller molecule. It has a lower range of motion, and it has a lower number of particles inside. So our X is going to be lower, and our N is going to be lower than the example on the right. Where due to the large size, we're going to have a greater number of N, and due to the ability of these bonds being able to rotate, of this molecule being able to shift around, we're also going to have a greater, I'll put it on this side, a greater number of positions with which these atoms can occupy as well. See, this is something we haven't really talked about quite yet, is the ability for bonds, is the ability that bonds have to be able to like rotate around. And so let's say we observe this chunk of the molecule all the way over here, this little branching like path. We can see that this bond right in here is a single bond. And single bonds are able to rotate, meaning that this entire winged branch of this structure is going to be able to rotate like so. This gives a huge range of motion for all of the atoms inside, the range of motion of which cannot be seen in this smaller molecule to the left. Therefore, large molecules, particularly ones with complicated bonding structures, are going to have an overall greater number of microstates for the particles inside of the structure, and as a result, a greater entropy. All right, so if we are faced with, a question of like, well, which is going to have more entropy, a single carbon atom or carbon inside of a molecule, we can answer that the larger molecule is going to have a greater entropy because of the greater number of not only particles, but the greater number of positions with which these atoms can occupy as the molecule moves around in 3D space. And even though this lecture was relatively long and involved as we started getting into the introductory material of being able to understand entropy, not just quantitatively through statistics, but qualitatively by observing our systems like molecules, the amount of molecules we have, the temperature of the molecules, I actually don't have any section review problems for you today. So I would advise you to read through the pages of this section, get a better idea for what entropy means and how it can be thought of. And when we come back together, we're going to be talking about the place of entropy in the universe. But until next time, class is dismissed.